So in the last section, we briefly talked about dependent and independent events, meaning in a sense, does something depend on something else? So as I had said, a simple idea is probability of A and B, so two things happening, is probability of A happening, and then probability of B happening, given that A has already happened. And as I said, B may depend on A or may not depend on A, meaning if I toss a coin for A and then roll a dice for B, the outcome of B, the outcome of rolling the dice, does not depend on tossing the coin. But how do we find out? Well, the idea is for independent events, so this is your test. To see if something is independent, probability of A and B is basically probability of A multiplied by probability of B. This is independent, right? Because this B does not depend on A. We don't need the dependence of A for B happening. So that's how we check. If this statement is true, then we are independent. If the statement is not true, then we are dependent. So this is basically the statement, right? B does not depend on A. So here we have a question about a store being expanded and the age of the survey respondents and so on. So what we have to find out? We want to know whether wanting to see the store expand is the same or is independent of being less than 10 years old. So maybe this must be a toy store or something. So first we'll ask ourselves, what is probability of A and B? So let's say we have to establish what's A and B first. So let's say A is less than 10 years old, okay? And B is saying yes, right? So yes to expanding the store and less than 10 years old. So A and B happening. So being less than 10 years old, right? Being less than 10 years old and saying yes is 0.27. Right. Is that making sense? All right. And then we have to ask ourselves, by the way, notice this is already in a relative frequency table. So we don't need to divide by the total here. So probability of A, which is being less than 10, is 0.36. Right? So these people are less than 10 years old. Right? And then probability of saying yes is this. All of these people are saying yes. And we can see that that would be 0.56. 0.56. And when you multiply this, you will see that it is not equal. You get 0.20. So this is not true. So here we are, not satisfied, right? So not satisfied. And so dependent events, meaning your age matters to whether you say yes or no for the store expanding. Now, sometimes it's quite obvious that an event is independent. Like in this case here, we have a spinner. You spin it twice, and you're trying to see what a probability is for a particular outcome. Obviously, if you spin the spinner once, and if it's a good spinner, the second round, the second spin will not depend on the first spin. And so in that case, you can just directly multiply. In that case, for a spinner, you can directly multiply A and B to get the probability of A and probability of B, because you already know that it is independent. Now let's look at a dependent event to see how this would make sense. So in this case here, we have $21 bills and 5 $10 bills. So let's make sure we know how many. So $1 bills are 20, okay, and $10 bills are 5, okay. You randomly select a bill from the bag and set it aside. Now that should give you a hint. If I've taken a bill out, now the original sample space is no longer the same. I originally had 25 bills in there. Now we only have 24. Find a probability that the first bill is $10 and the second bill is $10. So you know the second drawing is not independent. It depends on the first event because the sample space is no longer the same. So let's say A is first $10 and B is second $10 bill. Okay. Well, so probability of A and B. So remember the answer is probability of A happening followed by B, which depends on A happening. So given that A has already happened. So first let's look at A happening. What is the probability of me getting a $10 bill in my first draw? And that would be, we have 5 of them and we have 25 total bills, right? We have 5 $10 bills. I could pull any one of those 5 out of our 25 bills in there. Now that I've taken a $10 bill out, I only have 24 bills in there. And out of those, only 4 of them are going to be $10 bills, the ones that I want. And so now you can see how the dependence has changed the probability of finding a $10 bill because you've already taken one of them out. And this is what you are left with, 24 bills, out of which 4 are your interest. And then you can multiply this and you will get 1 over 30. Okay, so you have a 1 over 30 chance in pulling out 2 $10 bills in succession.